Alright, so today I want to go over section 11.5. Again, it's more, series. So in 11.5 we're going to talk about alternating series, and we're going to talk about absolute convergence. So after going over telescoping series, geometric series, and then we did integral test, and then nth derivative test, and alternating, now we're gonna go over alternating series test, absolute convergence, and conditional convergence. Okay. So up to 11.4, including 11.4, we went over series where the terms were always positive. In this section, we're going to divert from that. What if the tests are negative? How do we deal with those? Okay. So to deal with those, we're going to first talk about alternating series. What exactly is an alternating series? A series having either form. So when you say alternating, the signs alternate, plus minus, or minus plus minus plus. So if you have like a1 minus a2 plus a3 minus a4 plus negative 1 to the n plus 1 an plus, which equals sigma a n, negative 1 to the n plus 1 n equals 1 to infinity. Or it could be the first term negative and then plus, which would be negative 1 to the n instead of n plus 1, an, where an itself, the term itself is positive, but you can see it, it's a negative a1 plus a2 and so on, for n equals 1, 2, 3, and so on, is said to be an alternating series. So the signs do alternate in this case. Okay. There's what we call alternating series test, and that we're going to use to discuss convergence of certain series. Alternating series test. I'm going to use AST that as a acronym. So let an be positive, then the alternating series, whether it is the one that starts with a negative term and then they alternate, or the one that starts with a positive term and they alternate. Okay, what we do, converge. So the alternating series set converge if the following two conditions are met. If you take the limit as n goes to infinity of an and you get 0, so you take this term, you find its limit as n goes to 0 and infinity, and you get 0. And there's another rule: the terms of that sequence have to be decreasing for all n. a2 is less than a1, a3 is less than a2, and so on. So they're decreasing. And there's a nice proof in there, so in the notes, look it up if you want. If I ask proofs, it will be extra credit, okay? So here's some examples. So show that the alternating series converge or diverge, okay? The first one is sum from 1 to infinity, negative 1 to the n plus 1 over n. So an, this looks like an alternating series, but an is 1 over n, which is definitely positive. And it's decreasing. Why is it decreasing? And decreasing since, look at n is less than n plus 1. So 1 over n is greater than 1 over n plus 1. So an is greater than an plus 1, which means an plus 1 is less than an. Okay? And if you do the limit and n goes to infinity of 1 over n is 0, so we say series converge by the alternating series test. So what's required? Of course, you just look at an, which is 1 over n. So it's going to be everything except for that negative plus term. And so you're going to make sure that's it. And you're going to show it's decreasing, that sequence. And then the limit of an as n goes to infinity is 0. Once all this is met, then we say the series converges. Here's another example. Sum from 1 to infinity, negative 1 to the n plus 1, 2n plus 1 over 3n minus 1. As you can see, an here, it's not easy to... It's positive, right, if n is 1 or more, but how are you going to show that this is decreasing? I mean, it may not, it may. We have to do, it's not something we can compare. We have to find the derivative. Like we have to write f of x equals 2x plus 1 over 3x minus 1 and show that f prime of x is negative. Okay, so we have to do that, which may or may not be true. Not only that, we have to show that the limit of an is 0, but we know it's not 0, right? The limit, since the limit as n goes to infinity of an is limit as n goes to infinity of 2n plus 1 over n minus 1, which is 2/3. We say the series diverge. As long as it's not 0, we say the series diverge by the nth term test for divergence. This is the most handy test. This is the first test you should think about in determining whether a series diverges. If the limit of that nth term is not 0, then right away you say the series diverges. Okay? So we didn't need the alternating series test in this case. Sigma k equals 1 to infinity, negative 1 to the k plus 1, square root of k over k plus 1. Well, so the ak or an is root k over k plus 1, which is positive for k greater or equal to 1. It's decreasing because k plus 1 is actually greater than k. So 1 over k plus 1 is less than 1 over k. K is greater or equal to 1. So if you times by root k, which is positive, k plus 2, sorry, is greater than k plus 1. K plus 1. So this is a k plus 1. This is a k for k greater or equal to 1. So it's that sequence is decreasing, and the limit of k ak is limit k goes to infinity of root x root k, which is infinity over infinity. If you do L'Hopital's rule, you get limit as k goes to infinity. Derivative of root k is 1 over 2 root k. Derivative of k plus 1 is 1. 2 root k, which is 0 as k goes to infinity. So it's decreasing, and the limit, so by the alternating series test, series converges. Okay, example 4. Sum from 1 to infinity, negative 1 to the n over ln of n plus 1. Again, an is ln of n plus 1, which is positive if n is greater or equal to 1. And we also know that ln of n plus 2 is greater than ln of n plus 1, greater or equal, so 1 over an is 1 over, sorry. ln of n plus 2 is less or equal 1 over ln of n plus 1. So an plus 1 is less or equal an, so it's decreasing, and the limit as n goes to infinity of an, it's 1 over infinity, which is 0, so it converges by the alternate series test. Okay, number 5, sum from n equals 0 to infinity, negative 1 to the n over 2n plus 1 factorial. So if an equals 1 over 2n plus 1 factorial, know that an plus 1 would be 1 over 2 times n plus 1 plus 1, so it's 2n plus 3 factorial. We also know that 2n plus 3 factorial is greater than 2n plus 1 factorial, right? That's 2 more than that, so it's greater. So if you do 1 over, it's less than 1 over 2n plus 1 factorial, so an plus 1 is less than an, so an is decreasing, and if you do limit as n goes to infinity of an, it's 1 over infinity, which is 0, so the series converges by the alternate series test. Now there's what we call alternate series remainder, which is the error for estimating the value. If we cannot find the exact value of the series, which we can't for the most part in alternating series, then there's an estimate. And there's an error. If you use an estimate, there's an error. What is that error? It's called remainder, alternating series remainder. If a conversion alternating series satisfies the condition that an plus 1 is less or equal to n, so it's a decreasing, then the absolute value of the remainder, that remainder is called error, okay, Rn, involved in approximating sum of the series S by Sn. Sn, see, S is the sum of the whole series, Sn is the sum up to the nth term, is less than or equal to the first neglected term. So the difference between the actual sum and the estimate S is the actual sum and Sn is the estimate. That whole difference is the error, which is Rn, is less or equal the first neglected term. That's called the first. Why the first? Because we're using Sn, and Sn is what? A1 plus A2 plus A3 plus an. So you ignore everything after an. What's the first ignored term? Is the one after an, which is what? An plus 1. Okay? So here's an example. Number 38, page 7/7 in your text. Let's see what's 38 is about. Page 73, number 38. Okay, it says show that the series is convergent. So let's answer that question. Sum n equals 1 to infinity, -1. So it's alternating series, but it's a little bit tricky. So we're going to write this as -1 to the n to get the negative plus, and then 3 to the n should be part of the bottom. So an is actually 1 over n times 3 to the n. And that's the alternating term, okay? So, of course, n equals 1, 2, and so on. An obviously is positive, and if you do the next term, it's going to be 1 over n plus 1, 3 to the n plus 1, which obviously 3 to the n plus 1 is greater than 3 to the n. And if you times this by n plus 1, you times this by n, it would still be greater. If you do 1 over, it's less than 1 over n times 3 to the n. So an plus 1 is less than n, so the sequence is what? Decreasing. And the limit, obviously, limit as n goes to infinity, an is 1 over infinity, which is 0. So by the alternating series test, it converges. Now converges, I don't know what it converges to, okay? To some s, okay? We don't know that value s. That's the actual value that we don't know. Okay. Now it has how many terms of the series do we need to add in order to find the sum to the indicated accuracy? Okay, so we need to find n. That means the Sn to be used to estimate S if the error is less than 0.00005. So if I want to do S minus Sn, I need to find this n, find it, such that the difference in error is less than 0.0004 ohms, right? No, 3 ohms, not 4. 3 zeros. 0.0005. Okay. So if I want to do S minus Sn, what's the n that should be used? Well, if I key in, that calculator will help. Okay, so if I key in an, here I'll do it in front of you. An is 1 over. First, I gotta go to mode and make my mode instead of function, go to sequence like I did and highlight it and hit enter. Okay, and then go to y equal n minimum is 1. The sequence an is 1 over, and then in parentheses n times 3 to the power n, and then and the first term u of n minimum. So what's u of 1? The first, if you put a 1 over 1 times 3, so it's 1/3. So we gotta put that in here. So 1/3. And then go to table, second graph, and then you're gonna get, so the first term is 1/3 as we know, the second term is 0.055, third term is 0.01. So I'm interested in a number that's, when it reaches a number that's greater than the error. So if you look at A5, the fifth term, it's 8.2 times 10 to the negative 4. So you move the decimal 4 places to the left, which is still greater than 0.005. Right? 0.008 is greater than, so that's, so if you do A6, the sixth term, it's 2.3 times 10 to the negative 4, which is 0.0023 less than 0.0005. Okay, so that tells me, so okay, let's read this to understand what we're going to do. The convergent alternating series decreasing absolute value of the remainder involved approximating the sum s by Sn is less than or equal to the first neglected term. Okay, so that difference should be less or equal to the first neglected term, an plus 1. So this must be an plus 1, right? So an would be 5. An would be 0.0082, so n must be 5. So we gotta use the sum of the first 5 terms in order to get the error to be less than 0.0005. Okay. So now my next step in 11.5 is absolute and conditional convergence. Absolute and conditional convergence. Definition: if the series sigma absolute value of an of absolute values of terms converges, then sigma of the actual terms is said to be convergent absolutely, or absolutely convergent. So if you're doing sum of the absolute value of the terms and you get convergent, then that series sigma an is called converges absolutely. So the alternating series sigma n equals 1 to infinity, negative 1 to the n plus 1 over n 5 over 2, which equals 1 minus 1 over 2 to the 5 halves plus 1 over 3 to the 5 halves minus 1 over 5 to the 4 5 halves, and so on, is absolutely convergent or convergent absolutely, since if you do sigma of the absolute terms, it's gonna give you a sum of 1 over n to the 5 over 2, which converges C series where p is greater than 1. Since the sum of the absolute value converges, then the original value converges absolutely. And we have a theorem next. If series converges absolutely, that means it converges. And there's a nice proof that I have in the handout and in the notes, so check that out. So absolute convergence implies convergence. We're not saying if it's convergence, then it's, what about convergence? Does it give absolute convergence? We don't know. Don't know. Do not know. It may not. Okay? So far, that's what we know this way. If we can show that the sum of the absolute value of the terms is convergent, that means the sum of the terms is convergent. Now, conditional convergence. If sigma an converges like here, but sigma absolute an diverges. So if it converges but it's not absolutely convergence, that's what we're talking about. If it converges but it's not absolutely convergence, then we say it's conditionally convergence. Then sigma an is conditionally convergent. So if the original series converges but it doesn't converge absolutely, then it's called converges conditionally or conditionally converges. Here's an example. Sigma n equals 1 to infinity of negative 1 to the n plus 1 over n. This converges by alternative series test. Okay. Sequence is decreasing, positive, and the limit goes to 0, so it converges. But if you do absolute terms, which is sigma 1 over n, it diverges. It's a p series with p is 1. Okay, p series with p is 1. So that means sigma n equals 1 to infinity, negative 1 to the n plus 1 over n converges conditionally. Here's another example. Sigma n equals 1 to infinity, negative 1 n plus 1 over n root n. This converges since if you do absolute sum of absolute terms, it's sum from 1 to infinity 1 over n to the 3 halves. It's a p series, so it converges. Since it converges absolutely, then it converges. Okay, since sigma an converges absolutely, that means sigma an converges. Alright, sigma n equals 1 to infinity, negative 1 to the n plus 1 tangent inverse n. Remember I said the nth derivative test, the nth term test, if it's not 0, I know tangent inverse of infinity is pi over 2, so its limit as n goes infinity tangent inverse, which is tangent inverse of infinity, which is pi over 2. As long as it's not 0, we say series diverges by the term test. That's the easiest one if we can realize that. Here's another one. Sigma from 1 to infinity sine of 2n is 1 pi over 2 over n. Let's write out the first few terms to see what this is. If you put a 1 in there, sine pi over 2 is 1 over 1. If you put a 2, sine 3 pi over 2, negative 1 over 2. If you put a 3, 6, 5 pi over 2 is 1. So minus, which actually is an alternating series, so instead of this we can make it nicer so it doesn't scare you. Negative 1, since it starts with a plus, it's n plus 1, which we proved it is conditionally convergent. Why conditionally convergent? Because it converges but it doesn't converge absolutely. And that's it for 11.5. We will see you in 11.6.